Hello. So today we're going to finish off the booklet by looking at velocity time graphs. Now you've done speed time graphs, and you did them in second year as well, so you should be familiar with speed time graphs. So remember, speed time graphs tell you what speed you're doing at a certain time. Okay, so if you wanted to know what speed something was going at after 3 seconds, you read off the graph, and you read what speed it was going at. And for speed time graphs, there are certain rules that you need to remember. So you can work out the distance travelled by working out the area under the speed time graph. Remember when we were talking about these, I said that people always forget this rule. They always make it harder than it is. So distance travelled is the area under the speed time graph. So it could be that you've got a graph that looks like this, speed and time. And quite often it does this, then that. And you have to split it into sections, work out the area of each section and add them up. Another rule is acceleration is calculated from the steepness or gradient of the graph. So remember, acceleration is final speed minus initial speed over time taken. So you can work out the final speed from that point there, initial speed from that point there, and the time taken from the time. Okay. There are similar rules for velocity time graphs. And the displacement is the area bound by the area under the velocity time graph, and the acceleration is the gradient of the velocity time graph. So it's similar rules, but you'll see there's some slight differences with velocity time graphs that you need to take into account. So, example, a trolley changing a direction. So this example is if you think about a trolley going up a ramp. So you push it up a ramp, it moves, it starts off fast because you've pushed it, and as it goes up the ramp, it slows down. Then it reaches its highest point, and it just instantaneously stops. Then it starts to roll back down on itself. So you've got a trolley, you push it, and it goes in that direction quickly, but it slows down until eventually it comes to a stop briefly, and then it starts rolling back down again, and it starts increasing its speed back down the way. So it does that. Okay, so how do we show this change in direction? Speed time graphs don't show a change in direction, they just show the speed that it's travelling at. It doesn't show what direction it's going at. But we know velocity is a vector, so we have to know what direction it's in as well. Now, changes in direction are indicated by change in sign. So, in our case of the trolley, when it's moving in this direction, it will be positive. But when it's moving back the way, in the opposite direction, it will be negative. Okay, so we can see the graph here. So we say here, it starts off at 4 meters per second when you push it, and it slows down as it goes up the ramp until it's at the very top of the ramp when it reaches 0. Okay, so this is it slowing down. Reaches the top of the ramp, then it changes direction and comes back the opposite way. So, opposite direction. But it will speed up because it's going back down the ramp. Okay, so that's what's happening with this graph. So as it crosses the x-axis here, there's a change in direction. It means it starts going the opposite way. So in this example, find A part I, how far it's travelled up the slope. So how far it is travelled in the first direction. Then A part 2, how far it's rolled back down the slope. So how far it travels in the opposite direction, the negative direction. And part 3, the total displacement. So part 1, distance travelled up the slope. We want to look at this area here. So we want to look at what the area is under the positive side of the graph. So it's a triangle, so half times base times height. So half times 2 times 4, which is 4 meters. Now, how far it's rolled back down the slope is how far it's travelled in the negative direction. So we're looking at this area here. I'll just do a different pattern just so you can see the difference. Okay, so that area there, remember when I say area under the slope and under the graph, I mean the area bound by the graph. So it's not this part here, it's just the part that I've doodled in. So distance travelled down the slope, distance travelled in the negative direction. So it's that area with the dots in it. So it's half times base times height again. So half times 2 times minus 1, or 1 in this case, because it's just an area. So that's 1 metre. So total displacement, well, we just worked out that it moved 4 metres up the way, and then it moved 1 metre down the way. So remember, the displacement is from the start point to the end point. So that's our displacement. So it's 4 minus 1, which is 3 metres. And part B, the acceleration between 0 and 2 seconds, and then the acceleration between 2 and 4. So the acceleration between 0 and 2 seconds, we're looking at this line here. So initial speed is 4, final speed is 0, and the time taken is 2. So 0 minus 4 over 2, which is minus 2 meters per second squared. And that makes sense because it's slowing down, so it should be a negative acceleration. And the acceleration between 2 and 4, so we're looking at this line here. So final speed is minus 1, initial speed is 0, and the time taken is 2. So minus 1 minus 0 is 2, and it's minus 0.5 meters per second squared. The reason that it's minus is because it's going in the opposite direction. So a negative in acceleration could mean it's slowing down, or it could mean it's travelling in the opposite direction. Okay, so that negative also means opposite direction. Okay. Right, let's have a look at a couple more examples. So, motion under gravity. So we're looking at either a ball being thrown up or a ball being dropped, or an object. I'm just going to assume it's a ball. Okay, so we'll ignore motion B for now and we'll look at motion A. So an object is thrown upwards at 49 meters per second. It reaches its highest point after 5 seconds. Then it reaches a speed of 49 meters per second after a further 5 seconds on the way down. So what's happening? So I'm going to say it's a ball. It's being thrown up in the air, and then it comes back down again. Okay, so up and down. It's being thrown up at 49 meters per second, and it comes back down at 49 meters per second. At the very top, if you think about throwing a ball up in the air, you throw it up, it starts off fast, it slows down as it gets higher and higher, and then as it is at its very highest point, the speed is 0. Then it starts increasing in speed as it comes back down again, because it's being acted on by gravity. And we're told it takes 5 seconds to get to the center point, so that's 0. So a speed time graph would look like this one here. So it starts off at 49 meters per second, slows down to 0 after 5 seconds, and then it increases again its speed as it comes back down the way. A velocity time graph looks a bit different. So it's same on one side. So it starts off at 49 meters per second, decreases its speed as it gets to the very top. The speed is 0. Then it increases its speed, but in the opposite direction. So it's still increasing speed, but it's getting more and more negative. It's getting bigger, but in a negative direction. So it's decreasing speed here, and increasing speed in the opposite direction. So we can see that it has changed direction when it crosses 0. So it goes up and then comes back down again. For the other one, for motion B, we've got an object falling from rest, hitting the ground at 49 meters per second after 5 seconds. It then rebounds at 39 meters per second, coming to rest at its highest point 4 seconds later. So what's happening here? It starts off high up, it falls down, it hits the ground, and then it bounces back up again. Excuse me. So just before it hits the ground, it's 49 meters per second. And when it bounces back up again, it's 39 meters per second, because we know that, we've looked at bouncy balls before, we know that it loses some energy due to friction. Okay, and then it gets to its highest point before coming back down again. And we know that the speed is 0 at its highest point, and that's 4 seconds later. So it takes 5 seconds to get down the way, and then 4 seconds to get to that 0 point there. Okay, so it's a little bit more complicated this time. So what happens? Well, as you drop a ball, you know that it gets faster and faster until it hits the ground. So its speed increases to 49 meters per second. So it goes from 0 all the way to 49 meters per second. Then it bounces. So when it bounces, it's just very, very instantaneously at 0. Then it bounces straight back up to 39 meters per second. And as it goes up the way, it starts slowing down until it gets to 0. So we've got it speeding up as it goes down, and then we've got it slowing down as it goes up the way. So, velocity time graph. Again, the first part is the same. So, as it's going down the way, it's increasing in speed. So, increasing speed. And this is where it bounces. And then it comes straight back up, but in the opposite direction. So, opposite direction. And it's travelling at 39 meters per second and then slowing down until it gets to its highest point again. Okay. So, what is the acceleration of the objects during their motion? Well, to find the acceleration of their objects, all you do is b minus u over t. So for A equals b minus u over t. So if we look at this line here, the one that I'm colouring in blue right now, we can look at the final speed is minus 49. The initial speed was 49, and the time taken was 10 seconds. So minus 49 gives you, over 10 gives you minus 9.8 meters per second squared, which we know is to be correct because there's nothing else acting on it other than gravity, so it's accelerating due to gravity. B, we need to look at two different parts here. We can look at this acceleration here, and we can look at this acceleration here, because they will be slightly different. So let's call that I and that one II. So BI acceleration is v minus u over t. So final speed is 49. Initial speed was 0 divided by 5, which is 9.8 meters per second squared. Just increasing in speed. And II. So final speed in this case is 0 because it's decreasing to 0. So 0 minus the initial speed, which was minus 39, divided by 4. And that comes to, again, if you round it, 9.8 meters per second squared. So all acting under gravity, the acceleration due to gravity is 9.8 meters per second squared. Okay, I'm going to give you a video to watch, or I might get you to watch it before you even look at my video, just so you can sort of visualize these a little bit more, and then you can have a go at some questions yourself.